Welcome to another Sussex Universe lecture. Tonight we have Dr. Adam Barrett from psychology who's going to talk to us about quantifying consciousness.
For each of us, right here, right now, your conscious experience is all there is. Just what is it that is special about certain parts of the grey matter inside our heads that it gives rise to subjective experience? This question is sometimes considered the final frontier of science. Over the past few decades, a phenomenal amount of data has been recorded from our brains, and yet just a few scientists have been brave enough to try to use this to shed light on consciousness or to build credible theories. I would be humble and say I think we still know very little about this, but I am excited about some work that has been done in the last couple of decades that I think has yielded an unprecedented sequence of theory building that has received experimental support and led to clinical application. I'm always grateful to have a platform to talk about this because there has been a lot of misrepresentation on this. And I'd even go so far as to say that the very same scientists who've been responsible for some of this progress have perhaps sometimes been led on by the media to sensationalise or exaggerate where we're at. So just to say up front my answer to the question that's the title of this talk, can we measure consciousness? I think we're making progress on being able to assess how conscious an adult human is, given a recording from their brain. But to get to arenas other than the adult human brain, I think there's quite a long way to go. Just to introduce myself, I'm a mathematician by background. I'm now a lecturer in machine learning and data science in the Department of Informatics. And I have a doctorate in theoretical physics in string theory. And so it's with the perspective of someone interested in the fundaments of matter that I approach the question of the fundaments of mind. I'm also a more broad complex systems and data science person, and so I've put up a few other keywords there to just give you a sense of all my interests. So, consciousness. For me, the key to getting out of the philosophical quagmire and on to doing science is to realise that the question from a scientist's point of view is how and not why. So given consciousness exists, how is it generated? What type of process generates consciousness? I'm not interested in why should there be any consciousness at all in the first place. But of course, that's interesting from a philosophy point of view. And this question is interesting also to me because it's mathematically non-trivial, I think. So consciousness is not some simple function of the number of neurons that are active or the density of connections between the neurons or the overall level or intensity of neural activity in the brain. To give an example, the cerebellum here contains around 80% of the neurons in the human brain, and these neurons in the cerebellum are particularly densely connected to each other. And yet it's pretty widely accepted that the cerebellum plays very little role in generating our conscious experiences. On the other hand, there are certain parts of the cerebral cortex that play a very, very essential role in generating and shaping our conscious experiences. We want to know what is so special about these neurons and what they're up to. So the theory I'm going to talk about begins with a thought experiment that was performed by Giulio Tononi and Gerald Edelman back in the 1990s. And this thought experiment distills two key aspects of conscious experience, phenomenology, and goes on to assert that the neural underpinnings of consciousness must reflect these two key properties. So we're going to consider the conscious experience you have when you look at this picture. So the first thing to note is that your conscious experience is integrated, in the sense you experience this picture all of a piece. Your consciousness doesn't go through this picture pixel by pixel in analogy to a digital camera, and you experience a combination of everything simultaneously. You don't experience pure colour and then texture. All the different fragments of information are bound together into a unified whole to experience everything all at once. So, the neural dynamics underpinning a conscious experience must be binding different fragments of information together, and to do this, there's got to be a lot of connectivity between the different brain regions that are processing the different kinds of information, different strands of information. The second key property to note is that it is possible for you to have an extremely vast number of different conscious experiences. Although you've seen so many pictures before in your lives, you're all probably pretty certain that you've not seen this particular picture before, unless you happen to have been in one of my recent talks. So the theory says then that each conscious experience is extremely informative in an information theory sense, and that when you have a particular conscious experience, it rules out a vast number of a priori possibilities. This also means that the neural activity, when you're conscious, needs to be ever-changing, be able to explore a very wide range of different states, be rich and multifaceted, reflecting how rich and multifaceted your conscious experiences are. So in terms of the sort of architecture of neural connectivity, it's no good if everything's disconnected. You won't get any integration. And it's no good if everything is connected to everything else in a very homogeneous way, because then you won't get the diverse range of states accessible in order to have a large repertoire and to have rich and multifaceted consciousness. What you need is a good degree of connectivity, but inhomogeneous in connectivity, and to see a diversity of patterns when you look at brain recordings. So that's the theory. Now let's talk about experimental validation for this idea. So this has most famously come about through a series of experiments involving transcranial magnetic stimulation. In this paradigm, a magnetic coil is placed but just above the scalp and emits a series of very short magnetic pulses that trigger electrical activity across the cortex, and this activity is recorded in EEG electrodes distributed across the scalp. And the evoked response is analysed for participants in a range of different conscious states, from wakeful rest to deep sleep during the night to general anaesthesia under a range of different anaesthetics. And the common finding in all these experiments is that one does see a breakdown in what one could call integration and diversity in unconscious states compared to awake states. So when participants are awake, the response to the magnetic stimulation spreads far across the scalp. Activity shows up in frontal regions far away from the site of stimulation, and activity flickers on and off across the whole scalp for a pretty long time after the stimulus is delivered. On the other hand, when participants are unconscious, the response remains pretty local to the site of stimulation and dies out quickly. So there's a breakdown in integration of information between brain regions when you're unconscious. On the other hand, when participants are awake, you also see an analogue of this diversity, this richness, this existence of many states. What you see is very complex evoked waveforms that are very different at different electrodes. Whereas when participants are unconscious, you see a very stereotypical waveform that's not very complex in nature. It's just a down and up, down again, and then more or less flat. And even if you ramp up the intensity of the stimulus so you can get a slightly bigger response in a wider range of different cortical regions, you still see the same stereotypical waveform. So there's a breakdown in diversity of neural activity when you are unconscious. So this is validation of those two key properties of conscious experience are reflected in the neural dynamics. Now, Giulio Tononi, Marcello Massimini et al., together with Adenauer Casali, took this further to come up with a measure of consciousness that is indeed able to assess how conscious an adult human is when they take part in this experimental paradigm. To construct this metric from a recording from this experiment, what you do is you create a response matrix from the evoked activity. So you plot time on the x-axis and electrode number on the y-axis, and you decide at each point in this matrix, was that region showing significant activity above baseline at the relevant point in time. If it is, then you get a 1 in the matrix, and if it isn't, then you get a 0 in the matrix. Then you compress this matrix. Essentially, you look at how big the zip file is on your computer if you compress the file as an image file on your computer. Technical language, you compute the Lempel-Ziv complexity of this matrix. So the PCI index is the size of this compressed matrix. And this is maximized when you have both this integration and diversity of the evoked activity. If the response doesn't spread very far, then you have a lot of empty space in this matrix, a lot of zeros altogether, and you don't need very many bits of information. You can compress that down to just 1 bit, that region, because you just need to know the boundaries of this empty region of the matrix. So to get a large PCI, you need the induced activity to spread far. You'll also get a high value when the induced activity is inhomogeneous. So when it's not just everything becoming active and staying active, but you get flickers and different electrodes will flicker on and off at different times. If you get such a thing that's looking with a lot of different regions behaving differently, then that's going to be hard to compress. You're going to see a lot of different patterns. Now when this... so that's sloganized as zap and zip. You zap the brain with a transcranial magnetic stimulation, you zip the response, and that gives you your perturbational complexity index. And it turns out that this is a pretty good measure of consciousness with this particular calibration of this experimental paradigm on adult humans. You can more or less set a threshold that if the PCI is above a certain value, then the participant is conscious, and if it's below a certain value, then the participant is unconscious. As you can see, all these wake values for different participants are above about 0.4 here, and all the unconscious ones, deep sleep and anaesthesia under various different kinds of anaesthetics, they're all quite a bit less than that. This paradigm has been applied to intermediate states like sedation under anaesthetic, and it's also been applied to traumatic brain injury patients who are in coma or recovering from coma, and that's the clinical application, which I don't have time to go into, but it is proving useful at diagnosis and prognosis of such patients in hospitals. So yeah, this is all very exciting. So I'm delighted to share this with you. Right, so in Sussex, we've been looking at some slightly different data. That transcranial magnetic stimulation paradigm is assessing brain activity that's quite unusual. It's sort of sitting above our spontaneous brain activity. And actually, that evoked activity from the transcranial magnetic stimulation is not actually affecting consciousness in a huge way. That stimulation is not changing the consciousness of the participants. So we wanted to look at diversity of neural activity in different states of consciousness for just spontaneous neural activity to see if we can gain further validation of this theory of consciousness. So to do this, we analysed a rather special data set, which was even better than being able than analysing just scalp EEG. This was recording from depth electrodes that are inserted deep into the brains of some epileptic patients. These electrodes that are put there for surgical reasons, but then left in for several days. So we had a treasure trove of data recorded from a range of different conscious states. So we could have a few minutes from when participants are just doing wakeful resting, and the electrodes were of course in there all night. So we could have plenty of data recorded from deep sleep and dreaming sleep as well. For each participant, we had essentially a bunch of time series channels from a wide range of different brain regions, and these differed from participant to participant, and so we could explore what was going on fairly widely. And what we found was indeed a much greater diversity in the patterns of activity when participants were in wakeful rest compared to in deep sleep. Present a little animation to show a bit more extreme than what actually happened, but to give you to really give you the idea as clearly as possible. So when participants were unconscious, what we saw was a more reduced range of different coalitions of brain regions that would get active simultaneously. Might just be more or less the same set of regions that would get active at once. Whereas during wakeful rest, what we'd see would be a much more diverse set of coalitions of different regions getting active. First one, and then another. Each time, a different set of brain regions getting simultaneously active. So this was an indicator of the brain exploring a much more diverse range of states when you're conscious, and reflective of the fact that your conscious experience is very, very diverse and has a large repertoire. So there are our technical results. We applied 3 different measures of pattern diversity. There was again this Lempel-Ziv complexity. It's a measure of algorithmic complexity of a binarized form of the data. And 2 different measures of something called coalition entropy, amplitude coalition entropy and synchrony coalition entropy, which you can read about in a paper which was led by my former PhD student, Michael Sharpner. So in all 10 of the participants that we had, there was a very, very robustly measurable decrease in all 3 of these measures of diversity during deep sleep compared to during wakeful rest. These dark red ones are early night dreamless sleep, and the pink ones are later night dreamless sleep, or non-rapid eye movement sleep. So it's showing that perhaps there's an even greater loss of consciousness early in the night compared to late in the night. And interestingly, for dreaming, rapid eye movement sleep is when you're dreaming. There was not a significant change compared to wakeful rest. So that's indicative of you being conscious when you're dreaming. So sometimes it went up a bit. Some participants, it was lower during dreaming sleep. Overall, no significant difference across the 10 between wakeful rest and dreaming sleep. So these results were further validation of the theory. There's a breakdown in pattern diversity when you're unconscious during the night. For the remainder of the talk, I'm going to talk about integrated information theory, which takes this idea further. So we found evidence for a correlation between the level of consciousness and the extent of simultaneous diversity and integration in the brain. Integrated information theory starts from that same point, that same thought experiment, but then takes a logical leap to go further and state that everything is conscious to the extent that it is generating more information than the sum of its parts. I'll unpack that in the next couple of slides. What it does is integrated information theory attempts to provide a universal formula for consciousness based on the extent of this. So you could potentially use this formula to measure the consciousness, the amount of consciousness in any physical system. So what is meant by information here? Loosely speaking, if you were to record voltages from a bunch of neurons in the brain, you see how well you can use one result at the present moment to predict earlier and later results. And that reduction in uncertainty is the information there in the system. And crucially, integrated information theory tries to define this in such a way that the measure is observer independent. So Shannon information is usually you're talking about receivers and transmitters, and it's always reduction in uncertainty based on some prior information that the observer has. IIT tries to define this so that a priori the system could have done anything. It was in a maximum entropy state, and one has zero outside, the observer has zero information, and try to define it in such a way that it's observer independent. Then integration is the extent to which the whole is greater than the sum of the parts. So you compute the information for, say, the whole set of brain regions or every neuron considered together as one system. And then you partition the system and you compute this separately for parts. So you divide into parts that cover the whole system but that do not overlap. And then you make this comparison, and that's how you construct this phi measure. More technically, you're looking at posterior probability distributions for the whole and for the parts separately, considered in isolation. Or the probability distribution for the whole, how that differs in probability distribution space from the product of the probability distributions that you obtain for the parts. Now you can compute phi, say, for the whole brain, or theoretically at least, and you can compute it for subregions of the brain. And integrated information theory states that the set of regions with the largest phi is where consciousness resides. So, say in this sort of sloganistic toy depiction, the whole thing is scoring a phi value of 1. Whereas if you compute phi just for this bit that's more tightly connected, you get a phi value of 3. So the theory would say this is sort of the locus of consciousness. And then depending how the dynamics shift from one moment to the next, the actual regions that are responsible for generating consciousness can shift around from moment to moment. That's the theory. I think it's a very bold and exciting venture, but it does currently have many problems. there are too many possible formulae. So there's too many ways of putting this into mathematics, and there's no real way of arguing for one over the other. And these different ways of doing it behave quite differently in practice, even in simple toy systems. And all of them are intractable in practice. So you can't really compute this for any real systems. There's just so many different ways of defining information and of comparing the whole and the parts. What's lacking is a canonical, observer-independent way of doing this. Max Tegmark is an astrophysicist who's got interested in this. He tried to do a complete classification of phi measures that were compatible with the axioms of the theory, and it just sort of goes on almost forever. Different versions of phi. I've found a number of theoretical physics and mathematical problems with it as stands in a paper last year, which can be summed up as Einstein wouldn't yet be a fan of this. So I'm referring here to, just tying this in because this is a Sussex Universe lecture series. Einstein kind of knew that he was right when he wrote down his field equations before they were tested. I know that integrated information theory is not yet right. So none of these formulae are actually universally well defined. They were designed for to be applicable to systems where you've got a model system of interacting sets of logic gates, of discrete components. Like your physical system consists of discrete components that can either be on or off at each moment in a discretized time, and these interact according to update rules based on what was happening at the previous discrete time step. But that's not the way the universe is actually constructed. And if you try to apply it to systems for which you have a more general model, versions of phi that are proposed to be fundamental are not actually well defined, and I point that out in my paper. And none of these formulae are frame invariant. They rely on an observer's definition of the metric on probability distribution space. So, this is just, it's not working as a theoretical physics theory of consciousness. A more common critique of IIT is that it's panpsychist. I just mention this quickly because I don't think that's actually the problem. Let me just say a little bit. So yeah, there have been some silly articles on IIT talking about conscious spoons and measuring the consciousness of an iPhone and this kind of stuff. Again, I think this is hype. On IIT, saying we do swallow one of these measures of phi, it does posit minute amounts of consciousness, or at least the mathematical quantity that's associated with consciousness everywhere. So say an electron would be posited to be conscious of the direction of its spin, for example. But I don't think that's problematic. This is just ultimately then comes down to semantics. You could say, okay, well, if that's what IIT says, then maybe you want to say phi is measuring proto-consciousness. Use a new word. So an electron is proto-conscious of the direction of its spin. And then maybe you want to just remove that word proto only when the system gets very complex in nature. IIT does talk about the contents of consciousness as well as the level of consciousness. So we could talk about this shift from proto-consciousness to consciousness analogous to human consciousness without the word proto in front of it, maybe only when a system is integrating a lot of information about itself. So the theory could develop to get more nuanced, but the panpsychist critique I don't buy as being fatal. It's more these mathematical and theoretical physics critiques of this fundamental formula that for me are the problem with it. So it'll be interesting how integrated information theory develops if someone can make it more promising. I'll just end with saying I've considered, well, considering networks of discrete nodes or neurons as a fundamental description of reality of physics, that's not really fundamental physics. So to link integrated information theory with fundamental physics, I've postulated that it should be reformulated in terms of trying to have a formula that's applicable to an electromagnetic field. Because in physics, electromagnetic fields are actually fundamental physical entities. It's the fundamental field that's associated with the fundamental particle that is the photon. So on that view, you still need neurons. Neurons are the scaffolding that enable a very, very complex electromagnetic field to come into being. And the theory would say, I suppose, that any field, any fundamental physics, any fundamental field, the electromagnetic or any of the other fundamental fields in the standard model or beyond, any of those have the potential to generate consciousness. But you only get substantial or proto-consciousness, and then you only get consciousness like we know it when you get a very, very complex structure. And this is only possible in the very complex neural system. But in terms of coming up with a fundamental formula, maybe you want to come up with a formula that is observer independent, frame invariant, covariant theory, that could somehow get at the information that's intrinsic to an electromagnetic field configuration. I've got no idea how to do that, but that's my hypothesis about a possible way forward for integrated information theory. So, thank you for listening. The conclusion is that integrated information theory is exciting to contemplate, but has a long way to go. On the other hand, there is evidence that we're more loosely up the right track, that the neurodynamics underpinning consciousness reflect that conscious experiences are extremely diverse and at the same time integrated. So when you're conscious, your different brain regions are pretty well connected to each other, but not so pathologically that each part is prevented from processing its own different fragment of information. So there's a diverse range of information being processed and integrated across the brain. So I'll leave it there. I look forward to the Q&A. Just mention my collaborators. It was Michael Sharpner, my former PhD student, who analysed that data that I showed. And that data came from the University of Milan, from the Nobili and Massimini labs. And I'll mention Pedro Mediano, Anil Seth, and Lionel Barnett as intellectual inspiration and collaborators. Okay, thank you very much.
Well, we hope you enjoyed this video. Once again, I've got to ask, if you did enjoy it, please give the video a like and subscribe to our channel to see our future updates. If you're interested in the future talks we've got coming up, do visit our website at bit.ly/SussexUniverse. And remember, if you're watching live, the live Q&A starts now at the Zoom link in the description down below.